thus far, we were considering a simple, smaller cases of application of Kuhn-Tucker conditions. However, what we already said can be very easily extended to the case of n variables and m constraints. Okay, so look, how would the problem like this work out? We need to maximize a function of n different variables subject to m different constraints and, of course, non-negativity conditions. Look, even though this problem can be quite big, everything that we learned this far can be very easily extended to this case. What do we need to do first? Well, first thing, we need to form Lagrange function. Of course, so we use the original function, and here we will have sum of the product of Lagrange multipliers times the transform constraints that we have over here. And look, the next step is going to create two sets of conditions. First, we're going to have j different conditions based on the derivatives of z with respect to variables x, right? So, similarly, we require partial derivative with respect to xj to be non-positive. At the same time, we want xj to be non-negative, and of course, through complementary slackness, we require at least one of them to be equal to 0. And then, as we have m different constraints, each indexed by I, we will have m different partial derivatives of z with respect to Lagrange multipliers. And we require each of those derivatives to be positive, while to be non-negative, at the same time requiring Lagrange multipliers to be non-negative, and of course, through complementary slackness, we require the product of the two to be equal to 0, which means that at least one of them needs to be equal to 0. Okay, and look, this is not actually very different from what we already said. But what about minimization? For now, all we're doing was maximization, right? So how things need to change in order for us to be able to minimize the function. Okay, so then the problem would be stated like minimize function by x1 until xn, and of course subject to, and we will have a set of constraints. However, of course, as this is a minimization problem, instead of requiring constraints to be lower than some r, it is usually better to have them higher, requiring inequality that constraints higher than some r. Of course, look, it's never a problem with this because we can always multiply both sides of the inequality by -1, right? And any type of constraint can get into this form. Okay, and of course we're going to have m different constraints like that, each indexed by I, and at the end, as usual, non-negativity restriction. So what should we do next? Next, we should form Lagrange function. However, the Lagrange function that we had, for the maximization case is going to look exactly the same. So no issue over here. So at this moment, we are ready to define the Kuhn-Tucker conditions for minimum. Okay, now we need to make two small changes over here, and they're very small. First, now we will require the derivatives with respect to x's to be bigger than 0. And actually this is the only change. We still want x's to be positive, and still at least one of these expressions needs to be equal to 0. Of course, for every j from 1 to n. Secondly, we need to make this additional cosmetic change in the second type of conditions. So when we have derivatives with respect to Lagrange multipliers, and as you might guess, what we want right now is for them to be non-positive, right? While keeping Lagrange multipliers still positive and maintaining complementary slackness and requiring that at least one of the two expressions for each I needs to be equal to 0. Okay, and this is how we apply Kuhn-Tucker conditions for maximum and minimum. Okay, let me just clarify some things. I was not going through with you all those steps for minimization like I did for maximization, because the steps that are required would be pretty much the same. Of course, taking into consideration the fact that now we are looking for the lowest point and not for the highest point. Still, I would recommend for you, as a matter of practice, to do exactly what we did before, however, for minimization. It will show you that actually these conditions are the ones that we were looking for. Okay, now, one point of clarification: these are necessary conditions at best. Without saying anything else. Look, we still haven't said anything about second order condition. We have not provided conditions that would tell us that whether this is a maximum or minimum, any additional tests. However, in the context of nonlinear programming, we are doing it a little bit differently, because those conditions are already different for maximum and for minimum. There are two problems with that, and one of the problems is that we're going to, that sometimes constraint can provide us with some issues. And those issues can be avoided when we use a test for constraint qualification, which we will do in the last video. Secondly, there are theorems that actually allow us to say when those conditions, so when Kuhn-Tucker's conditions are actually sufficient for maximum or minimum. Again, this is going to be a topic of our last video. Those conditions are unfortunately very long, a little bit boring. We need to be aware of them. However, you can be sure they are not on the test. So, knowing that, there is one thing that definitely needs to be done at this moment, and those are examples. So look, in the next two videos, we're going to consider maximization problem and minimization problem, because the way of solving those is a little bit different of what we are used to, because we need to go through trial and error in order to get this solution. We're not just we are not just setting derivative up to a point, creating a system of simultaneous equations and solving. Here we need to actually work a little bit more and be aware which restrictions hold, which restriction is not binding, and making sure, of course, that the results we are getting are not negative. Okay, so thank you for your attention and see you in the next video. Take care.